Okay. Something we haven't talked about, but you can check out on your own time, is the fact that you can also parallelize DNSSEC. So you can make the requests in parallel. So far, we've been showing that the requests happen one after the other, but you could make requests in parallel to speed things up. You can also validate signatures in parallel. So instead of working your way up the chain like we've been seeing, some of it can be done in parallel. That speeds up DNSSEC. Enough said about that. Another class of things we have to worry about when we're implementing DNSSEC are implementation errors. DNSSEC on paper, as we've designed it, does achieve our security goals. But even if it's perfect on paper, if you go into the real world and you implement it wrong, you mess up, you might be losing some of the security that you had. So some possible examples of people messing up, even though the protocol itself was designed securely. You might claim to support DNSSEC, even though you don't. Now you're tricking people into thinking that the records are secure, even though they're not. You might change your key, but forget to update signatures. You might present signatures that are old. These are all issues that might cause DNSSEC to not be secure, even though it is secure in theory. So those are some things you might have to watch out for if you're deploying this as a name server yourself. And this has actually happened before. We'll not read this out loud, but there have been cases where people tried to implement DNS, but they did it wrong, and users kept seeing errors, or they thought they were secure, but there actually wasn't security. So something to watch out for, and it has hit major companies before as well. So you don't have to know all the little implementation details. We'll just tell you one that you should know, and it's the fact that recursive resolvers and stub resolvers are two different things. Remember, we showed you the picture where a user, like my computer, making a DNS request, usually just makes the request to the recursive resolver. The recursive resolver does all the talking to other name servers, gets the answer, and then gives the answer back to me, the stub resolver. So one common point where people mess up is they have the recursive resolver do all the validation, and whatever the recursive resolver returns, our computer just trusts. So we ask for the question to the recursive resolver. We tell the recursive resolver to do all the work, validate all the records, send us back the final answer, and whatever answer we get, we just trust. Well, now we've introduced a security vulnerability. If we're not the ones validating the records and we're making the recursive resolver do it, the recursive resolver itself could send back poison records, and we would trust them because we're telling the recursive resolver to do all the signature verifying for us. That only works if you trust the recursive resolver. If you don't trust the recursive resolver, then you're in trouble. So if you really want DNSSEC to provide the security that it promises, you have to verify the records yourself. Your computer should be doing the verifying. You shouldn't outsource the verifying to someone that you don't trust. That's an example of the scheme being secure in theory, but not in practice if you forget to actually verify the records. OK, that's it for DNSSEC. The idea was kind of beautiful. It was the idea of using signatures to verify records and using a public key infrastructure, in other words, certificates where you endorse the next name server, to delegate trust starting from the root and spreading that trust down the tree. Then we saw how it's actually implemented in a backwards compatible way. Everyone sends their public key using the DNS key data type that's new. And when you want to delegate trust to the next name server, you use a combination of DS and RRSIG types. Those two types combined delegate trust from the parent name server to the child name server by signing the child name server's public key with the parent name server's private key. And anytime you have a final answer, like the A-type record, you attach an additional RRSIG type that signs the answer. And you don't have to know the exact details, but we did see at the end that zones get split up into key signing keys and zone signing keys. And we finished by showing another clever design where we used NSEC to sign ranges of domains so that we could prove non-existence in an efficient and secure way. That's it for DNS. It's a very cool topic. Hope you enjoyed it. Coming up next is firewalls and denial of service.